Sodium can be brought in sticks or in coils. You can see the coils over here, and bricks. It's on ingots. And in tanks, suppose you want a large capacity tanks, 40 tons rail tanker, and sodium tanker of 20 ton also is available. And this sodium, it's highly reactive. This molten sodium, you can see how it is reacting with air, oxygen in the atmosphere, and forming into sodium aerosols, white color aerosols are formed. And this rapidly burns in air, and it forms dense white smoke of sodium monoxide. And you just leave it, a sodium brick, which was left aside for some time. You can see how you just totally gets converted into sodium oxide. And this sodium reacts readily with oxygen in the air. And this is the basic equation where sodium reacts with oxygen, forming sodium oxide. And so it is essential to store and handle sodium under a special protective cover. Normally, if it is in the form of bricks, either a wax coating is provided on the surface, or it can be covered with plastic or polythene sheet, and it is kept in drums, stored it, sealed and kept in drums. Other option is go for a tank with inert atmosphere over the sodium. This inert atmosphere, it can be either argon, helium, or nitrogen. And you will be remembering in our, when we are doing our plus two, and also sodium was stored in kerosene in our laboratories, chemistry laboratories. Normally in our large sodium system, argon is used as cover gas, and this prevents air ingress into the system. So reaction of air with sodium is avoided. And sodium also reacts with moisture very rapidly. You can see a very large violent, its reaction is very violent. And this can evolve hydrogen, and this hydrogen, it can be, this becomes highly explosive. And you can see some photographs of I'm showing where sodium reacts with water in a small quantity of, in terms of grams, milligram level. We have put it in water. You can see a fire. This is due to the reaction of, it's highly exothermic, and it catches fire when it sees water. And the other product is sodium hydroxide and hydrogen. This hydrogen is evolved when there is a reaction of sodium and water. And coming to the reactor program in fast breeder, we are having in KALPAKKAM, in IGCAR, we are having one reactor called fast breeder test reactor. It's a 40 megawatt thermal, 13 megawatt electrical, plutonium uranium mixed carbide fueled, sodium cooled loop type reactor. And this reactor has been in operation for more than 30 years. And its main aim is to generate experience in operation of fast reactors and sodium systems, and so serve as an irradiation facility for development of fuels and structural materials for future fast reactors such as PFBR. The total sodium inventory in habitat is around 150 tons. You can see the number. It is 150 tons of sodium, which needs to be handled safely. And it is, even though it is within a very large containment or a vessel, and it is safely held inside the vessel, and argon is provided as inert gas over the top. Second is the large reactor, which is being commissioned now, prototype fast breeder reactor. It's a 1200 megawatt thermal, 500 megawatt electric, plutonium uranium oxide fueled, sodium cooled. It's a pool type reactor. This is a prototype reactor. This will demonstrate the feasibility of operating indigenously designed and built fast breeder reactor in India. The total sodium input, you can see it's around 1650 tons. So containment of such a large amount of sodium, in fact, in the main vessel, it's around 1200 tons. Very large vessel of 13-meter diameter and 13-meter tall. So within that, we have to contain such a large quantity of sodium. And so you can see the magnitude. It's around almost 10 times that of fast breeder test reactor, the quantity of sodium which is being handled in our fast breeder prototype fast breeder reactor. See, this sodium, it's hazardous if it leaks out. In air-filled enclosures of FBRs, care must be taken to prevent leaks to the atmosphere. This sodium systems, normally they are made of stainless steel. It's total piping, it's totally large vessels and components are there where sodium is filled. And this sodium, it is a totally welded construction, and there is a possibility of leak. And this leak may occur from a high stressed weld joint or thin membrane. There are a lot of membranes, members, which I'll come to the individual things in my subsequent slides. And there are bellows This may fail. The thickness of bellows is only 0.3 mm, and there is a failure of bellows may lead to sodium may come out. You see, just a large quantity of means like 200, above 200 or 300 sodium. Once it comes out, it will catch fire, and this generates a lot of white smoke. These sodium aerosols are highly irritating. When it comes in contact with our eyes or throat, it can there is an alkali burn within our throat and all, and it's going to affect your throat. And when there is a large quantity of smoke, it even reduces the visibility. Hydrogen is evolved and sodium reacts with moisture. So this important thing is you have to avoid sodium coming in contact with air or moisture. This extent of hazard depends on many factors. The size, it tells us what is the quantity of sodium which can leak. Location also, location is an important factor. Temperature. See, sometimes even at low temperature like 200, it may not catch fire. It'll just come out and it can stay there as a liquid, and slowly it becomes solid. It solidifies in room temperature. Slowly it gets cooled and becomes solidified. The condition of surrounding air, like the humidity within the area and proximity of personnel, how many equipments or personnel are nearby, there may be they may also get affected. And this may lead to sodium fire and subsequent issues in the plant. Next is around, this is one incident. I'll just come to some incidents. There were a lot of incidents, which had a very big impact on the sodium cooled fast reactors. Like one incident was a leak from a thermowell. You know, thermowell is a tube sort of arrangement. This is the tube sort of arrangement where a thermocouple is introduced. This thermowell tube failed, and around 600 kilograms of sodium had leaked out. This is from a reactor, Monju reactor in fast feeder reactor in Japan. That was an incident, and this is an own incident at fast feeder test reactor, and where a valve got a small pinhole through this pinhole. Sodium had leaked out. This is a blind hole, and you can see the quantity of sodium which had leaked. Around 75 kilograms of sodium had leaked. These are all some major incidents which had occurred worldwide. Like I said, already said, Monju, BN 600. And with respect to reactors, these are the major ones. And ABTR also somewhere around 75 kilograms. Remaining things are from experimental facilities. The quantity of sodium leak were large. They were experimental facilities. With respect to reactor, it is this is the maximum around 1 ton of sodium. And one thing is most of the incidents of sodium which had leaked, they had leaked into a double envelope, and it was not a major accident except for this Monju where the sodium had leaked out and affected the structural material also. And there are some incidents that happened in our experimental facilities. You can see the pinholes is the bellows, and is the pin tube sections where small sort of a maximum of 3 kilograms of sodium only had leaked in these systems. One of the important issues is sodium fire protection. Is how do you prevent a sodium? We need to take utmost care in prevention of any sodium leak. There are methods which are adopted during design itself. Design of sodium systems a minimum number of components. We have to reduce the number of components and pipes, and design concepts, sound design concepts based on international codes, and tested materials which are qualified, and austenitic stainless steel is the major material which is being used, and welded construction. There are no flange joints in the system, and limit the number of welds. Most of the weld joints shall be away from the most stressed zone. Nozzle penetration below the sodium boundary is also avoided. And helium leak tight construction with respect to quality assurance of the system. And walls are double metallic bellowed walls where there are twin plied walls, bellows. So there is no possibility of sodium coming out in contact unless or otherwise the bellow fails. And free level concept with inert gas. Sodium is always above the sodium pool. There is a gas space, and most of the pumps and all centrifugal pumps, free level concept, they are used in tanks which are having gas on the top. And direct contact of leaking sodium with concrete. See, concrete reaction is quite severe. So special type concrete are being used for sodium systems. And sometimes we provide even carbon steel liners where the sodium will not directly come in contact with the concrete. And venting system with filtration to remove smoke and aerosols to prevent settling of aerosols, and so that firefighting personnel can enter and fight the fire. And we don't use for water. There will be no water inside the sodium system building. It will be away from the sodium system area. And control cables shall be coated with fire retardant material, fire barrier in the buildings. Eye and body wash. This is important with respect to any, suppose there is a spillage of sodium coming in contact with personnel. For the first aid treatment, we provide eye and body wash very near to the sodium area. And for mitigation or extinguishing sodium fires, adequate quantity of dry chemical powder, which is the basic material for extinguishing a sodium fire. And with respect to the radioactive systems, we are having double wall arrangements. There is no chance of sodium coming in contact with the atmosphere. And with respect to detection, see, this is one of the major things with respect to a sodium system. We are having sensors throughout, like throughout the pipelines or components. Leak detectors are provided. So in a very, very small quantity of leak also, it can be detected within a very, very short time. So we are using wire type leak detectors, which are laid throughout the pipelines and components. And spark plug, simple spark plug has been converted to suit to our sodium leak for our sodium leak detection. For bellows seal valves, there is a port where sodium spark plugs are provided. And overall, suppose there is a leak and there is a fire, there is a smoke detector. We call it a sodium aerosol detector or ionization detector, which takes care of which is where the in the field the aerosol is continuously sampled and analyzed through a sodium ionization detector. And this is the leak detection system where you can see wire type leak detectors laid throughout like beads. This is a bead arrangement. A single wire in a bead laid throughout the pipelines. If there is a leak anywhere, this wire will get earthed. This is pipe is earthed, and there is a shorting, and immediately you get an alarm, and we can take action within a very, very short time. And this is the for the spark plug. I said this is the port where the spark plug is introduced, and this bellow fails. Immediately, the spark plug, there is an extending rod which will detect the sodium leak, and it gets we get an alarm in the control room. And these spark plugs are also used in some sodium heat exchanger, fin tube sections, etc. This is the aerosol detector. You can see the detector unit where the sodium it's having a hot filament, and for forming sodium plus ions from the elemental or compound sodium in the gas. And these ions, there is a background value in the atmosphere itself. So when there is a rise in background, immediately you get an alarm that there is an aerosol. Sometimes even for weld fumes also this one will work. But sodium, we are at any way it will work for sodium smoke also. And third one is the suppression part, where we are provided catch pans or stained carbon steel trays below the sodium systems, so that any leak, it should not, the sodium, suppose there is a leak from the pipelines or components, it should be contained in a tray. So there are sufficient quantities of catch pans provided below the sodium systems, and dry chemical powder is stored all around in the building. It is almost the quantity will be almost 4 or 5 times the normal requirement. So almost like if suppose 1 kg of sodium leaks, around 5 kilograms of dry chemical powder will be stored. Then exhaust fans will be provided in the sodium system area, and so smoke can be diluted so that people can approach the sodium fire. And so this is the major thing. And next major issue in any sodium cooled fast breeder reactor is a sodium water reaction. This steam generator of fast breeder reactor is having water on the tube side, and the shell side is its sodium. The water is at high pressure, around 17 megapascal, and the sodium is at around 0.4 megapascal. And suppose there is this water, the tube failure, steam will come into sodium, and immediately there is a reaction of sodium water reaction happens. And this is the reaction, and very high quantity of you can see that it's highly exothermic, and this forms into hydrogen. So this we are able to, we have to detect this at a very incipient stage. And there are different types of leak. There's very small micro crack, we say, in the milligram level leak also can be detected by the sensors, which are very sensitive in the sodium system. You can see how the jet comes and in attacks the adjacent tube. Failure of multiple tube also is possible, but provided this hydrogen sensors are working properly, the very short time we'll be able to detect the a steam leak into sodium. And these are all some sort of what sort of the magnitude of leak, less than 50 gram per milligram per second, more than 50 milligrams per second. We call it by different names: micro leak, small leak, intermediate. These sort of leaks are possible. So for everything there is a protection system available. And this is some experimental and observation on a steam generator tube. These are all sensors. Different types of sensors are used in for hydrogen detection in the sodium system, where hydrogen meters for in sodium detection of hydrogen. Suppose there is a steam sodium reaction, and this hydrogen can be detected by in sodium meters. And at lower temperature, operating temperature, hydrogen in argon detectors are provided. This electrochemical hydrogen meter is also one which has been developed within IGCAR, and this is used for detection of hydrogen in sodium at very high temperatures. And these sensors can detect the hydrogen concentration at an order of ppb level also. So coming to sodium fire, and you can see the color of sodium fire. The basic difference between any fire is a general fire and a sodium fire is the color. It's golden yellow in color. With a lot of only difference here, you can see it's blackish. So it's due to the carbon here. Here the carbon content is very less, and sodium, it's pure sodium. It's almost less than 25 ppm, 30 ppm of carbon only is there in the sodium. That's what is the purity level we maintain. And but the issue is white dense smoke, aerosols. And this sodium, when left open to atmosphere, is oxidized spontaneous with evolution of heat at room temperature. And but this cannot be termed as fire since oxidation is very low. As sodium temperature is increased, the rate of oxidation is also increased, resulting in sodium catching fire. So sometimes I said already, as I already said, almost 270 to 300 degrees centigrade, the temperature is raised, and if it leaks, sodium will catch fire immediately. And combustion and flame temperatures, suppose there is a sodium fire, the temperatures may be of the order of 650 to 870 degrees centigrade, right on top of the pool. And it's it did not radiate, because people can approach, the personnel can approach very near to the sodium fire and extinguish it. The sodium combustion is always a production of heat, light, smoke, and flame. The severity of consequence of sodium depends on the temperature, degree of dispersion, sodium to air ratio, heat transport properties, and its contents. Aerosols, you can see the white dense aerosol, and this contains a sodium oxide, sodium hydroxide, sodium carbonate. When it goes above, it becomes sodium carbonate, highly irritating in smell. It can affect our eyes, throat, etc. And these are all some sort of experimental numbers with respect to ignition temperature of sodium. Fine particles of condensed sodium, I mean, it's like vapor mists, even ambient temperature. Well, it depends upon the surface area. At ambient temperature, it can catch fire. Sprayed droplets, wet and dry air at 120 degrees centigrade. A solid jet of sodium issuing from pipe or vessel at 200 also it can catch fire. Disturbed pool of sodium at 200. You cannot rub. Suppose sodium is hot. You just give some friction, it can catch fire. Or using a stirrer, you stir it, it can catch fire. Okay, and this is about the ignition temperature. These are all some types of sodium. This is a spray fire, and this is a pool fire. You can see jet of at a higher temperature when you send out the sodium. You can see it is an experimental setup where the sodium catches fire immediately when it sees oxygen. This is a pool fire, and this is you can see a jet fire coming out into a tray and getting collected in a tray. And this is a comparison of sodium fire and an oil fire. You can see this is an oil fire. You see the length of flame or the height to which the flame goes, and the sodium, you can see very in terms of centimeters only. Sodium flame rate is an order of magnitude lower than that of liquid organic fuel. Ignition, combustion, self-extinction behavior of liquid sodium differs drastically those of conventional oil fire. And this the ignition temperature is sensitive to moisture content. Suppose there is a higher moisture content, then also the ignition temperature can vary. And heat release rate of is 15 times lower than, you can see that, you can see the number 15 times lower. That's why people are able to go very near to the sodium fire for extinguishing it. Sodium fire must be extinguished by, this is about passive sodium fire protection systems. You can see these are all some tray arrangement, which was, as I said, covered trays are available, provided all around. Like this is called a corrugated tray, and this is a conical tray, and these are all provided below the sodium pipeline or components. It comes here and it goes down, and oxygen is cut off. So by just cutting off oxygen, this fire gets extinguished. And this is called oxygen starvation or blanketing. And this have such type of trays have been provided all below most of the large containments. And this is the second one, as I showed. This is the indigenously developed leak collection tray at IGCAR. This also has been tested for its performance in the experimental setup. This is how sodium, suppose it leaks, it will in the leak collection tray, it is getting collected in a tank. So there is a fusible plug, sodium leak will go into the tank and safely, this is under argon or nitrogen atmosphere. This is the tray which is provided below the experimental facilities. Sodium fire mitigation, with respect to sodium fire mitigation, it should be ensuring oxygen starvation. Catch pans, as I showed below, are provided below pipelines. Sodium resisting concrete, liners, carbon steel liners, etc. And the sodium fire depends upon many factors like temperature, oxygen, moisture, form, liquid, or it's a pool or spray fire or pool fire, velocity of air over the surface area, depth of sodium pool. And you can see how sodium fire simulation, we have simulated some sodium fire heated using a gas torch during a firefighting drill, and you can see how the sodium in a tank it was heated, and at 500 degrees centigrade it was allowed to jet out in a tray. Active systems for sodium fire extinguishment, evolution of large amount of white oxide smoke during a sodium fire can, this is reduces the visibility. This sodium fire, white smoke will, densified smoke will cut off the visibility. So we have to cut off the source. The most easiest way is cutting off the fuel. In our secondary systems and all, the sodium can be drained into a tank. So you cut off, that is the fuel here. Sodium is the fuel here, or you can close a wall, whatever is. Normally what we do is, if there is a leak, drain the sodium, totally cut off, remove the sodium from that area. And then we have to fight the sodium fire. So it falls into a tray. This tray is provided to contain the sodium fire. And sometimes even inert gases, suppose you don't have anything, inert gases can be used for cutting off the oxygen on the surface of the pool. And many experiments were done with respect to the fire extinguishers. These are all the types of extinguishing powder for sodium fire which have been used. Sodium bicarbonate, so HCO3, it was the standard sodium extinguishing powder. And these are all some later developments like ternary eutectic chloride, sodium chloride based powder, and Graphex powder. Testing was done, and you can see the sodium bicarbonate was quite good. There was no splattering. The powder flowed. The powder, actually, the density of powder needs to be less. Density of sodium is 900 kg per meter cube. So the powder of the powder density should be less than that. So for it to cut off the or blanket or air oxygen starvation. And there was no reaction with sodium bicarbonate and sodium up to 350 degrees centigrade. And the quantity of sodium needed was also less. And this is non-toxic, free-flowing. When you are making the extinguisher come out of an extinguisher, the free-flowing nature is very, very important, and it's very, very cheap, around 60 rupees per kg. And this is the standard specification for a trichemical powder used in our sodium systems, like the sodium bicarbonate, magnesium stearate, magnesium carbonate, tricalcium phosphate, etc. And see the moisture content. This is very, very important, and the cooling rate also. This one, suppose there is a sodium leak, we are tested on sodium leaks where the powder was, the cooling rate was also observed, was quite good. And these are all some new powders which have been being studied upon. And this is about ternary eutectic chloride. This has been developed by ISRO, patented by ISRO. It's available in market. It's quite good. It's having a slightly higher density, but it cuts off the, so we extinguish the sodium fire very effectively. and it's used for very useful, suitable for sodium. It has been tested and being used now. And these are the physical properties or the specification for ternary detector chloride based board. It's having barium chloride, potassium chloride, and sodium chloride in various ratios. And magnesium stearate is one which prevents the hygroscope, improves the hygroscopic, non-hygroscopic nature of the powder. And this is a graphics which has also been it's also available in market, and it's also was quite good, has been tested. You can see a fire created and extinguishing also has been, you can see here. And the specialized graphite powder, you can see around 88 to 95% is the graphite powder. Aluminum, magnesium, aluminum silicate, 3 to 8%. Magnesium stearate is the third one. Magnesium stearate is added in all the powders to prevent the moisture ingress into the powder. And these are all standard extinguishers which are going. It's a 10 kg extinguisher, 75 kg extinguisher used in for experimental facilities. For the large reactor, it's in terms of tons, around 10 tons of extinguishing powder is stored in large tanks. And this manually it has to be expelled from a nitrogen system. You pressurize the nitrogen and the powder comes out, and it can be used for extinguishing the sodium fires. And this is a loose powder in a extinguishing powder in a box and a tray. This is one of the best ways of extinguishing a sodium fire, because you can approach it very easily, except for the aerosol. You have to cover your eyes and make oxygen available for yourself. SCBA devices has to be used to reach the thing, and use a loose powder to extinguish the sodium fire. These are all basic types of fires. Like ordinary combustible, we use class A, class B, class C, class D. This is what is class D is the one which is used for sodium fires. These are the extinguishers, different types of extinguishers. You can see the dry chemical powder cartridges. And this is for carbon dioxide. One important thing is carbon dioxide, it should not be used for sodium fire. Water, carbon, no other powder or more liquid can be used on sodium fire, because it can catch fire. Challenges in handling sodium fire is entering to a sodium fire building is very hazardous. Like there is a very large fire, and you have to take care of yourself. Personal protection is very, very important, provided you are having personally protected with a SCBA device, and two persons need to go to attend to the sodium fire. Visibility is one important issue. Breathing support is required. And this sodium, when it comes in contact with body, it can give an alkali burn. And we can use this sodium dry chemical powder, dry sodium bicarbonate based or ternary detector chloride to extinguish the sodium fire. These are all some sketches, means photographs which were being taken during extinguishing a sodium fire. And next, coming to handling this sodium, actually, suppose we are going for any maintenance requirement. Suppose you want to need to replace the components. So we need to cut the components for removing it. For that, there are certain methods by which we are cleaning the components which are removed. And this is one way, where the pipelines which are filled with sodium can just put it in a thermofluid oil bath at a higher temperature on 150 degrees centigrade. The sodium goes into the oil. This oil is an organic oil. It doesn't have any reaction with it, is inert towards sodium. So the sodium thermofluid oil is one. Second one is alcohol. This is very, very much required. Suppose I am cutting a line, I have to clean the pipeline for introducing another one. Suppose a wall fails, removing the wall and putting a new wall. The pipeline has to be cleaned with alcohol and thoroughly removed. Sodium has to be removed. Particles of sodium has to be removed. Then only welding has to be taken up. So this alcohol is used for the cleaning purpose. And finally, this disposal of sodium, waste disposal, can be done by using water. Because water, sodium becomes soluble in water, and it can form sodium hydroxide and hydrogen. But there are some disposal yard, where the sodium can be disposed. So important points to be followed while handling of sodium are: knowledge of the physical and chemical properties of sodium in which it is handled is necessary. This decides the potentialities of the reaction. Where appropriate protective equipments, have approved extinguishing materials at hand. Never use water for firefighting. Store sodium in well-labeled rust-free metal containers away from water, and inspect the containers periodically for integrity. Plan the disposal of sodium residue in advance in designated places remotely located. Do not allow waste sodium to accumulate. And these are all some safe personal protective equipments which are used in for sodium handling. Helmet with face shield, fumes mask, high temperature. This is high temperature gloves. PVC gloves is used for cleaning. and gumboot, air respirator, particulate shovel, etc. And this is a very, very safe method of disposing. Suppose sodium leaks in a system, you have to, there is a lot of scavenging work involved. This sodium has to be removed, and you have to collect it in trays and charge it into vessels, which is heated by simple supply of air. This sodium is heated, and when the fire, it gives away aerosols, and these aerosols are sent through scrubber systems, and finally the aerosol which comes out it will be as minimum, that it will be totally diluted, and it can be sent into the through the stack to the atmosphere. And this contains a venturi scrubber, a quench tank, etc. And this aerosols will get diluted and finally collect in a scrubbing solution tank, where the pH more than, when it crosses 10, we have to remove it and put it into a pit where it has to be neutralized for sending to the atmosphere. And these are all some first aid for sodium. Sodium, actually, when it falls on the body, there is as I said, there is an alkali burn which is possible. So we have to remove the clothes. As much as particles of sodium can be, sticking sodium can be removed. And water. Now water is going to help you a lot, because it will reduce the heat burn to the body. So continuously flush with water and shift the injured person to the first aid center or hospital. This is how it is done. Okay. This is about a minor chemical burn. This is a standard chemical. Remove the, suppose sodium is spilled on your body, remove the shirt or lab coat, and then wash wherever the particles are coming in contact, wash thoroughly with the water. And this is for first aid for eye. This is very, very dangerous. Suppose it falls on the pupil of your eyes are gone. So suppose a small particle of sodium falls on your eyes, continuously flush with eye wash. There is an eye wash. Keep your eyes open. Allow the water to continuously dilute the sodium, and finally shift the person to through an ambulance to a hospital. So that's it about sodium safety or handling in our reactors and spindle systems. Liquid sodium is the best coolant of choice, that I already said, and due to its favorable nuclear, physical, and chemical properties. Its high chemical reactivity towards air and water necessitates special design features, which have been which comes under the prevention category. And handling aspects and risk involved in handling are thoroughly understood, and more than 35 years of experience which have been gained is very useful for our handling of sodium systems. Thank you. Any questions? Hello. Hello. Any questions, please?
Audience, questions, please. Unmute your mic, and then you ask questions. Okay, no question means we will move on the next talk. Thank you, Chandramouli, giving the highly knowledgeable and
good evening, sir.
Good evening.
Yeah, my name is Dulab Das.
Tulak Das.
I have one question. Yeah, I have one question.
Question is there. 1 minute. Yeah. I give it to speaker.
Yeah, tell me, sir.
Sir, actually, in our village area, once we are something burning in our hands, suppose to hot water put in our suddenly it's happened in our hand.
Sodium. You're saying sodium leak in your body.
No. I'm just telling about the hot water, just normal hot water.
Normal hot water
falls
on your
our hand or whatever. Okay. So we are applying some sodium salt. We are using the salt. So how much it will be logically?
First is you have to cool it. Actually, before applying anything, it is advisable to cool it. You need to continuously keep in cold water. That is requirement. Because this heat burn, I have seen a person who was, in fact, hot water fell on his body. The injury was very severe. But the immediate action, if you just go to the shower and cool it, that heat burn is affects you more than any other. Instead of applying any sodium powder or anything, just cool it. That's what is followed in our sodium system. It's an hydroxide, because when it comes in contact with body, there is a lot of moisture. This moisture reacts, and we are having sodium hydroxide, an alkali burn, and this heat. If there is heat will affect your skin. It can just this skin. So better is, before applying any powder, we, unless or otherwise we are very sure with respect to the first aid, don't do it. Shift the person to a first aid center or the hospital as early as possible. That's what is my observation in many people. Injuries have happened where the sodium also has fallen on the body of a person, and he was taken to first aid, and he was the injury was not very severe. Clean with water, and it was not severe.
So immediate effect should be that it should be keep it cool place,
cool
right?
Only. Yes.
Okay. Thank you, sir. Thank you for this answer.
Any more questions? There are no questions. Thank you, everybody. Thank you for listening to my talk. So that's it.
Thank you, Chandramouli, giving the highly energetic and highly knowledgeable sodiumized talk for our engineering community. Thanks, one and all. We will move to next session. Before that, we will honor the speaker on behalf of IEI KLC, our token of our love. We will give one small memento. Sharing, slide sharing வரணும்ல. போட்டாங்க. ஓகே மேடம். ஓகே வந்துச்சு.
Hello. Okay.
Please start, madam.
Hello. Sir, whether it is audible?
Audible, madam, audible. Please start.
Sir, is it audible?
Audible, it is audible.
Okay, sir. Okay, sir, I will start.
Please.
Good evening, everyone. Of SS304B4 stainless steel using standard austenitic consumable, which has very low cracking susceptibility. So I'm Divya, working as a scientific officer in IGCAR in materials joining section. So in this course of talk, I'll be covering these points. First, I'll be giving a short introduction on the borated stainless steel and the weldability issues associated with that, and experimental methods that we used in the study, and discussion on results and recommendations for welding this borated stainless steel, and a demonstration of improved weldability of the new procedure we have adopted to weld this borated stainless steel, and finally the conclusions. So now coming to a short introduction of our prototype fast breeder reactor, and this is the view, a schematic view of the PFBR. This PFBR, this is the main vessel, and for our PFBR we have a lot of components associated with that, and some of them are listed. There is a main vessel, a core, a grid plate, inner vessel, and heat exchangers, sodium pump, this safety vessel, control plugs, and roof slab, etc. And these components are mainly made up of 316 Ln austenitic stainless steels, and this is more compatible with the liquid sodium that is used as a coolant in this reactor. And in the previous talk, sir has explained us the importance of sodium that is used in the PFBR as a coolant. And here, particularly my area of interest is the intermediate heat exchanger that is here. That is the intermediate heat exchanger. The function of this component is to transfer the heat from the primary sodium to the secondary sodium that is flowing inside it to the heat exchanger sodium to water heat exchanger system. So the secondary sodium that is flowing inside this heat exchanger should not come in contact with the primary sodium, because the primary sodium is highly radioactive. So therefore, the heat exchanger that is there inside the reactor, the part of which is exposed to the core of the reactor. This is the core of the reactor, and that area which is exposed to the core of the reactor is covered with a neutron shield. So that neutron shield is basically made of the borated stainless steel, because the neutrons from this, in case there are a lot of safety aspects that are provided within the core, and if there is a chance for this neutron leakage from the core, and it should not bombard the secondary sodium that is flowing inside the heat exchanger, intermediate heat exchanger. So we have a neutron shield over here in this area of the heat exchanger. So here you can see the schematic view of where this borated stainless steel is shielded to the intermediate heat exchanger. This is the location of the core of the reactor, and this is the side that is facing the IHX, that is facing the new reactor core. And here is the borated stainless steel sheet provided. So in our PFBR, 304B4 grade SS containing around 1.24 weight percentage of boron is used for construction of these neutron shields for this IHX. Basically, this neutron shields are fabricated by welding. Just it is strapped on to this intermediate heat exchanger on that side. And the importance of this work is that the borated stainless steel exhibits poor weldability because the boron that is present in this borated this stainless steel has very low solubility in the austenite matrix. So now let me introduce this borated stainless steel and the weldability problems associated with that. Borated stainless steels are general class of austenitic stainless steel that contains around 0.2 to 2.8% of natural or enriched boron. This is because the boron is a good neutron absorber. That is, it has a very high cross section for thermal neutrons. any neutron that is coming and bombarding the component, it can absorb the neutron by a very N-alpha reaction. The neutron is not allowed to enter further. So these stainless steels are typically found in applications such as nuclear fuel storage racks, spent fuel transportations, and neutron shielding applications. So now coming to the weldability of these borated stainless steel, that is, this subject is very important because most of the components are fabricated by using welding processes. So weldability, what does that terminology mean? Is that weldability is that ease with which a material can be welded. So that is, it should be welded without any defects, and also the welded component should serve in the desired functions for its design life. So weldability of any component is very important. In this case, the solubility of boron in austenite is only very negligible, that is around 100 ppm. So this boron, what happens is during this welding, material is melting and resolidifying. So what happens is this boron, because it is insoluble in austenite, it gets segregated to the grain boundaries and interdendritic boundaries during solidification, and it forms low melting eutectics. That is, it forms some compounds that enlarges the freezing range of the metal. So when the freezing range is enlarged during solidification, there are a lot of shrinkage stresses acting on this weld metal, and because of this enlarged freezing range and shrinkage solidification, the material is prone to crack, and this cracking is referred to as hot cracking. So generally, in any austenitic stainless steel, the basic weldability issues will be hot cracking, distortion, etc. So in this material, so similarly, because we have more amount of boron in this austenitic stainless steel, solidification cracking is a major issue. So this solidification cracking or hot cracking can manifest itself at different locations within a weld metal. That is, a solidification cracks that is formed in the weld metal itself, and liquefaction crack can be found in the base material also and previously deposited weld metal, and a ductility dip cracking is found slightly away from the weld metal heat affected zone, etc., in the base metal. So these are different forms of hot cracking that is found during welding of any stainless steels. So this is the photograph of the intermediate heat exchanger during fabrication. You can see it is a big structure, and this borated stainless steel neutron shields come somewhere in this region, which is facing the neutron reactor core. So generally the understanding from the literature is that borated stainless steel containing more than 0.58% of boron. That is, already I have told that this class of steels contain 0.2 to 28% of boron in it. So the steels which has more than 0.58% of boron are considered to be easily weldable than the stainless steel that has less than 0.58% of boron. So in our case, 304B4 grade stainless steel has around 1.28% of boron. So it was considered to be fairly weldable. So during fabrication of this neutron shields for this IHX, we have chosen boron-free E309 electrodes. As we all know that 309 electrodes are very versatile. And for any dissimilar welding, this 309 electrodes are chosen to minimize the risk of hot cracking. But what happened is that during fabrication of these intermediate heat exchangers, using this 309 electrodes, extensive cracking was observed during welding. Though we have chosen a base metal which is not very easily vulnerable to hot cracking, and also electrode which is very versatile, which can culminate hot cracking in the weld metal. Even after taking so much of precautions, we found extensive cracking during welding. So more than 100 test coupons were actually made using different electrodes, but then also we could not get satisfactory welds while using this 309 electrodes or any other electrodes for this. So we had to go for 8 BRN, that is 308 electrode containing boron, around 1% boron in it. So this is a non-standard electrode, but we could achieve near satisfactory welds only by using this type of electrodes. That is like not in satisfactory weld even after using a customized electrode. So the basic aim of this study was to understand the hot cracking behavior of the steel during welding with boron-free E309 electrodes and boron added consumables. Even with boron added consumables, we like faced this hot cracking issues, but comparatively less. So in that case, to find out the mechanism for this hot cracking occurring in these 12 months and also to recommend a suitable procedure that can be for hot cracking. So this aim was achieved by sequentially creating like achieving certain objectives. That is, first we studied the hot cracking behavior of boron containing electrode and compared it with the boron free electrode. And we did extensive characterization of weld joint microstructures for understanding the mechanism of cracking, and then to recommend a suitable solution to mitigate the hot cracking during welding of these borated stainless steels. So this is the experimental methods we have used. Here is the composition of the borated stainless steel. This is covered under ASTM's specification A887, and this is the specified limit for
screen out ஆயிடுச்சு. ஷேர் பண்ணி அத பாருங்க. அவங்களுக்கு வெளியில போயிடுச்சுல. நமது ஷேரிங் மோட்ல நமது ஷேரிங் மோட்ல தான் இருக்குல்ல. ஓகே ஓகே ரீகனெக்ட் பண்ணுங்க. ஓகே ஓகே நான் சொல்றேன்.
Hello. Hello, sir.
ஷேரிங் எல்லாமே இருக்கு. உங்களோட பிபிடி எல்லாம் ஷேரிங்ல தான் இருக்கு. நீங்க மட்டும் லாகின் பண்ணுங்க உள்ள வந்து.
Tamil sir, you can present, I think.
Fine, fine. Thank you, thank you. Can you see me, sir? No, I'm not able to share my screen.
Yes, sir.
It says the last is the last presentation over.
Not sure. Sanmugan sir.
Sharing is disabled.
Sanmugan sir.
I think the presentation is not over, the last presentation.
Okay, sir. Then wait.
Got abruptly cut off.
Yeah.
Okay, no problem. I can wait, no problem.
Okay, okay. That's what they did in sharing option, I think. Okay, sir.
No problem, sir.
Thank you, madam. Yeah, not completed.
Very good, madam. Please continue. Madam.
Yeah, madam.
Audio. Madam, please continue.
Hello, sir, is it audible? So mechanical properties were evaluated as for tensile test, impact test, and micro hardness using weaker hardness testing machine and as per standards. Hello. Share agliya. Ipa parunga.
மைக் மட்டும் அன்மியூட்
Madam, it is visible, madam. Screen is visible. Proceed. Thank you.
So this is the variscent setup. Here it is autogenous TIG torch, and we keep our specimens over an anvil, and there is a die block underneath the specimen. And when this TIG, this automated autogenous TIG welding is carried out over the specimen, when the TIG torch is coming to the center of the specimen, this anvil is this die block is activated using a ramp to bend the specimen during the weld solidification. So by this way, we are actually externally imposing the restraint on the solidifying weld pool, and this way we are evaluating the hot cracking susceptibility of the material. So this is the variscent test method, that is variable restraint test method. So we have several variations in this variscent test method. Like we have spot variscent test method. In this method, we are evaluating the HAZ cracking susceptibility, that is a weld spot is created and the HAZ formed surrounding the weld is characterized for its susceptibility for cracking. And a longitudinal test, we see the weld metal as well as HAZ for cracking susceptibility, that is the direction of welding and direction of straining are in the parallel direction. And in case of transvariscent test, the direction of welding, direction of the applied bending strain is perpendicular. So in that way, the weld center is targeted and we evaluate the weld metal cracking susceptibility. So the strain augmented on the specimen is calculated by this formula T by 2 plus RT, that is T is the thickness of the specimen, R is the radius of the die block, and by changing the die block radius, we are changing the strain imposed on the specimen. So from this experiment, we will be getting the maximum crack length, total crack length, and brittleness temperature range. These parameters are used for evaluation of the cracking susceptibility. Maximum crack length is calculated from the surface of the fusion zone, that is tested specimen. We have some cracks forming on this specimen, and what is the length of the maximum crack that is formed on the weld metal. So this one is used as a criteria for evaluation. One more thing is the total crack length. We will calculate the sum of all the cracks that are formed on the surface of the weld fusion line. And brittleness temperature zone is a separate, there is a separate module to determine this brittle temperature range for this experiment. And some parameters that we use during the variscent experiment is shown here. Like current, like for this variscent experiment is carried out for partial penetration weld. So for each material, the current voltage that is applied will change. Like we don't want a complete penetration weld, but a partial penetration weld, and speed is fixed, and arc length, shielding gas is used as argon shielding gas, and we apply augmented strain starting from 0.258% up to 4% strain by varying the die block radius. So next is the way to determine the experiment is completed. Hot cracking variscent experiment is completed. We again load the specimen, a normal sample, untested specimen, and during using the same parameters that we have used for the variscent test, we keep a autogenous weld bead over the specimen. And during weld is happening, we insert a thermocouple connected to a data logging system. And by this way, by the time the thermocouple is inserted in the fusion zone, the arc is switched off. Here we are not going to apply any strain by using the die block. And from this thermocouple, we are measuring the thermal profile of the cooling weld metal. So for this experiment, we use a C-type thermocouple because we are putting the thermocouple in the fusion zone, the temperature can be very high, some few thousands of degrees Celsius. And from the maximum crack length, we have determined from the Varistant experiment, the MCL is like superimposed on the temperature gradient profile that we are obtaining from the cooling profile from the by inserting the thermocouple. So here we take maximum crack length and we impose it on the thermal gradient, and from this we determine the initial temperature at the fusion line as well as the temperature at the crack tip. So this temperature where the crack is propagating, the range of temperature where the crack is propagating, the brittleness is very high. That is, the material does not have any ductility, literally brittle. So this temperature range is known as brittle temperature range. That is also a criteria for evaluating the hot cracking susceptibility in the material. So now coming to the borated stainless steel base metal, for this we have simulated some solidification behavior for this material using thermocal software. Here, this is the equilibrium phase diagram calculated for this particular composition for 1.224 weight percentage of boron. And here we can see that the solidification range is very narrow. But when we are going for a non-equilibrium solidification simulation, that is in case of weld metal, which undergoes fast heating and fast cooling process, the method, the solidification scheme that is adopted is a non-equilibrium process. That is, there is no sufficient time for diffusion of all elements to take place during solidification. So there is a lot of segregation involved in this solidification process. And for this material, when we do a non-equilibrium solidification simulation, we see that there's abundant amount of liquid, more than 50% of the weld metal fusion zone is with liquid. So this we can see from the green line. So during non-equilibrium solidification, your solidification range is increased around 130 degrees Celsius. Earlier, if it is going through a normal equilibrium solidification mode, it is only 90 degrees Celsius. What is the significance of this non-equilibrium solidification with a higher solidification range is, for this is because during non-equilibrium solidification, the more is the freezing rate, higher is the time that is spent by the material in the mushy zone, that is solid plus liquid region. So your grain boundary is all fully in the surrounded by liquid eutectic components. So basically you have a larger chances of cracking with a higher solidification range. So now coming to the microstructural studies of this borated stainless steel. See, this is a base metal microstructure. Here, this is the austenite matrix. You can see the grain boundaries of the austenite, and here these black color particles are the borides. That is, we have this boron added to this austenitic stainless steel because there is low solubility of this boron in the matrix. These are coming out as boride precipitate during solidification. So these are borides. So when we during welding, these things are going into liquid stage, and again it is solidifying. So now we can see that in the fusion zone, the morphology will be different. So now we have extracted these borides from this matrix, and we have characterized these borides. What kind of boride? What is the composition of these borides? So we did XRD to confirm that these are chromium borides. These are basically chromium borides. They are rich in chromium. So we have done TEM also to confirm this. So now coming to the fusion zone, when the material is being welded, it is going to liquid state and again resolidifying. We have this type of microstructure. We have austenite dendrites and this interdendritic region where you have this fingerprint type of structure. They are all eutectic constituents. And this is a SEM image of that, and we have a magnified view. Here we see these are all boride eutectics that is present in the interdendritic regions of these austenite dendrites. And we have different morphologies of these eutectic borides. And we have again extracted these borides from this fusion zone. And again, we have characterized these borides. And we could see that they are not only chromium borides, CR2B type of borides, and there are of different stoichiometry. And we have analyzed this through XRD system. So this is like, we can see M23B6, Fe23B6 type of borides are formed. And again, there is FeB type of borides are formed, Fe2B type of borides are formed, in addition to CR2B type of borates, we are having different stoichiometries and different varieties of borates in the fusion zone. So we have also confirmed all these different borates using TEM also. So what we can infer from this study is that the borates that is formed in the fusion zone of borated stainless steel is different in composition and morphology as compared to the base metal borates. So now coming to the solidification cracking susceptibility of this base material. If you see, when we did that Varistant experiment on the base metal, that is when once the 304B4 material was solidified, we see that these whatever cracks this region are getting backfilled by the eutectics that are formed in the fusion zone during solidification. You can see these dark black regions are the cracks, and these were backfilled to some extent by the eutectics that are formed in the fusion zone by capillary action. So this is what is protecting the material from the hot cracking that we have seen already. Though cracks are forming, these eutectics are getting filled in the cracks, and thereby it is healing the cracks that are formed. So during the experiment, we found that there were no negligible number of cracks on the surface of the fusion zone. So these were seen only at a very high magnification, not using a stereo microscope at a 6 times the magnification. So these were considered to be immune to hot cracking, as we have seen in the literature. Literature also reports the same, like more than 0.58% of boron containing stainless steel are immune to hot cracking. But in the even in the case of liquefaction cracking, as I told you, it is occurring in the base metal side in the HAZ. So there also we see that these hot cracks that are formed during experiment are getting backfilled by the eutectics from the fusion zone as well as the eutectics in the HAZ of this borated stainless steel. So when we evaluated, we saw that in the PMZ, that is HAZ, we see that there is little tendency for hot cracking, but not very high. Generally, total crack length, if it is more than 4 mm, at 4% augmented strain, we take it as the material is more susceptible to hot cracking. If it is below 4 mm, we consider it to be negligibly susceptible to hot cracking. So in that case, we say that borated stainless steel base metal are immune to hot cracking. This is in line with what we have found in the literature also. So now we see that it has a good resistance to borated base metal, has a good resistance to liquefaction cracking as well as solidification cracking, and this is because of the backfilling of the eutectics that is happening in the fusion. Now coming to the scenario where we are welding this borated stainless steel using a boron-free consumable, that is 309 weld metal that does not have a boron. So here we see the microstructure of this weld metal that was welded using joined using 309 weld metal without any boron. So this is a boron borated stainless steel base metal having micron sized boron in the matrix, and this is the partially melted zone where these borides are melted, but austenite matrix is intact. And we have another zone called unmixed zone because of the variation of the melting point between the welding consumable and the base metal. We have an unmixed zone, that is the material is not fully mixed. The base metal is not fully mixed with the consumable, that is weld metal. So here we have just the borides and the boride interdendritic borides and the austenite dendrites. And slightly inside in the region of C, we have base metal diluted 309 weld metal. Here the base metal is diluted by the weld metal is diluted by the base metal, that is boron from the base metal is entering the weld metal. And far away from this zone is the region C, where it is interior to the weld metal center almost. We see only the austenite dendrites and the interdendritic delta ferrite. This is a microstructure. Here it does not contain any boron from the base metal. So this is a basic microstructure. So to determine so here we can see that this weld metal diluted by the base metal is more vulnerable to cracking. So to determine the cracking susceptibility of this region, we have made weld joints like this, and we have extracted hot crack specimens from the weld joints, and we have made a spot Varistant experiments in this region that is near to the weld interface where this base metal dilution is there. So we have taken again extracted the specimen from the weld joint, And we also tested the specimen at the weld center where there is negligible base metal dilution. So let us see the results from this experiments. Here, this after doing the spot varistate test, we have seen that where we tested at very near to the weld interface, we see the very high cracking susceptibility, whereas at the weld metal center, we see very negligible cracking happening here. So this is the macro structure where we have did experiment near to the weld interface, that is where this base metal dilution is there. So here we see very large cracks on the surface, and where this there is negligible cracking, here we don't see any cracks on the surface of the weld metal. So when we did the detailed microstructural analysis of this specimen, this is the tested specimen. We see these cracks here at certain region away from the weld interface. So whether cracking has happened near to the weld interface where this base metal dilution is more, yes, this is the microstructure where this has been taken very near to the weld interface. It is not that cracking has not occurred. This shows that cracking has occurred, but it is getting backfilled by the eutectic near the weld interface because it is very close to the base metal. Here there is partially melted zone. This whatever liquid is formed here is backfilling the cracks that is formed near the weld interface. But these cracks which are slightly away from the weld interface, we can see that the cracks are open and very prominent. And when we did SEM analysis at this region, we found that there are thin films of eutectic that is present along the grain boundaries. These thin films are very fine, that they are not sufficient enough to backfill these big cracks. So they are very fine and they are very flimsy. So these thin films of borides were present when during our microstructural analysis. And very far away from this region, we can see that the other side, very near, closer to the weld center, we see that there is no borides and there is only austenite and delta ferrite. That is, this 309 electrode, when it solidifies in a ferritic mode. That is, first phase that is formed is a ferrite phase, and it has a duplex microstructure, that is delta ferrite is there in the austenite matrix. So here in this region, because there is no borides, there is no cracking. Here there are borides, but sufficient borides are there to backfill the cracks. So here there is no cracking. But in this region, cracking is very vulnerable because there is only thin films of borides that is not enough to backfill. So this is the reason why we found cracking in the weld joints where we used the 309 electrodes for joining this borated stainless steel. So to calculate what is the boron content in this region where it was vulnerable to cracking, we did some SEM analysis and we have done this dilution study. From the dilution study, we have back calculated the boron content in this region. That is where the region, where the dilution content is around 13 to 18% in this region. Here, the boron content is falling below 0.5 weight percentage, and it is between 0.5 to 0.2 weight percentage boron. And where this region, it is very vulnerable to cracking, as we saw earlier in the literature, that any boron containing stainless steel containing less than 0.5 weight percentage of boron is prone to hot cracking. So this is also in line with this. So because of base metal dilution, we are having some region in the weld metal where it is falling, where the boron content is falling below 0.5 weight percentage, and it is prone to cracking. And this is very obvious, like the reason for cracking in this weld joints. So what is the purpose of going for then 309 electrode, which has sufficient amount of delta ferrite? Here, because the boron content is very high, though ferrite number in this region is around 11 ferrite number, even then the cracking is occurring. This is because the boron also has very low solubility in ferrite, delta ferrite, that is present in the 309 electrode. So the delta ferrite or ferritic mode of solidification that is there in this 309 electrode is also not helpful in mitigating the hot cracking in this borated stainless steel. So now we can see that boron, why these 309 weld metal is more prone to cracking because of base metal dilution. So the weld metal, which is undiluted by the base metal, is not susceptible to cracking because there is no boron, which is highly diluted by the base metal, where boron content is higher than 0.5 weight percentage, is resistant to cracking. And the region where it is falling between 0.5 to 0.2 weight percentage of boron, there it is highly susceptible to cracking. So now now we have seen while using how this cracking is occurring while using non-boron free consumable. Now let us see what is the performance of the boron added consumable. So these are the macrostructures of the tested specimen at various strain levels. You can see that if you are increasing the augmented strain, the crack width and length is increasing. So, but it has certain cracking resistance up to 1% augmented strain. That is, if you are going beyond 1% augmented strain, the material is prone to cracking. So here we can see the macrostructure. We can see that the finer cracks are getting backfilled because it is borated electrode only. It is having around 1 weight percentage of boron in it, and it also forms eutectics and forms the liquid that can backfill the cracks. But the liquid volume that is formed in this borated electrode is very limited. So it cannot backfill all the cracks as that of 304B4, that base metal we have found. Here we are seeing unfilled cracks that are open at a higher augmented strain. So this material, when we tested, we also saw that because the total crack length is above 4 mm, is also moderately susceptible to cracking. That is, whenever we want to use this electrode for a application where lower restraint, that is geometrical restraint or thickness of the base metal that is to be welded is smaller, we can go for this electrode because that restraint expected in those components will be low. So this will serve the purpose. So in that way, it is moderately susceptible to cracking. So this is because, like as I explained, like what is the volume of eutectic liquid that is forming, it varies with boron content. With a higher amount of boron, we have a large amount of liquid fraction. With decreasing boron content, we have decreasing eutectic liquid that is formed. So that is not sufficient for backfilling to occur. So now we have seen that borated electrodes are also serving the purpose, but it is not like very highly resistant to hot cracking. So now coming to the mechanical properties of this borated stainless steel given by ASTM standards, we can see that borated stainless steel 304B4, which is used for our PFBR, it is giving a certain requirements for elongation, hardness, and impact toughness value. But in this case, we can see that there are two grades of stainless steel, grade A and grade B. Whatever we have used for our PFBR is grade B material. Grade B material is nothing but grade A material is manufactured by powder metallurgy route, but grade B material is used by our general ingot solidification technique. Here, because it is used like produced by grade A material used by powder metallurgy route, you have a spheroidal borides, and it has a better toughness as compared to the grade B material. So in that case, for applications where we are going for grade A material, the impact toughness is a mandatory thing. So now we can see how these weld joints are performing in the mechanical property requirements. So now we can see that these are the results of the tensile properties. That is, one is this red one shows the base metal tensile property. It has a good elongation. When you go to this weld you prepared using non-boron free electrode, that is 309. We can see that it is like both are deteriorated. It is not as comparable to the base metal, but it has adequate strength. It has borated electrode has a very good strength, but boron free electrode has an adequate strength. When we see the micro hardness results across the weld joint, we see that the 309 boron free electrode has a more or less uniform hardness distribution across the weld joint. In case of boron added electrode, we have a higher weld metal hardness as compared to the base metal because of borides present in that. So now coming to impact toughness, we see that this boron added weld joint has a very low impact toughness because it is fully eutectic borides, very brittle in nature, and so impact toughness is low. The base metal has around 20 joules impact toughness at room temperature, whereas in case of 309 electrode, which is boron free, and the notch is put at the center, we have a higher impact toughness value. So this E309 electrode can be used where impact toughness requirement is mandatory for welding this borated stainless steel. So hence, now let us compare weld joints of this borated stainless steel prepared using boron free electrode as well as boron electrode. In case of E309 boron free electrode, we see that it is very highly susceptible to cracking because of base metal dilution. In case of boron added consumable, it is moderately susceptible. In case of boron free electrode, it has adequate strength and good impact toughness. In this case, where this boron is added, it has good strength but very poor impact toughness. And also in case of boron free electrode, we have seen that it is because of only base metal dilution we are ending up with high cracking susceptibility, and we have a very good scope to improve the hot cracking susceptibility resistance of this material. But here, whatever we have seen for boron added material, the scope is very little to improve because weld metal composition cannot be changed at that for the particular electrode position. So now we are going for a procedure, a modification to curb the hot cracking that is happening while welding using E309 electrode. See, because we see that base metal dilution is playing a major role in increasing hot cracking susceptibility. We are using this 309 electrode to butter the surfaces that are to be joined, because during buttering we have base metal dilution in the buttered layer, but we don't have any restraint because we are not joining it with any component. The restraint there is very minimal, though we have weld metal interdendritic liquid constituents present in this region. We don't have any restraint involved, so the cracking tendency is very low. We have already seen that hot cracking occurs only in the presence of low melting eutectic liquid in the fusion zone, as well as restraint, that is shrinkage stresses or any geometrically developed restraint in the structure. So here restraint is very low. So the probability of cracking is very low. We have to give a sufficient buildup such that there is base metal dilution on the surface of the edge to be joined is almost zero. So next we are going to use the same E309 electrode to join the buttered surface. So while joining, you have the restraint arising from the geometry and solidification. But here the interdendritic liquid, that is this boride eutectic, low melting eutectic, that is coming from the base metal dilution is not present. So here we are having restraint but no liquid material surrounding the interdendritic boundaries. So in this case, we are able to curtail the hot cracking that is formed in the during welding of this borated stainless steel. So this we have demonstrated. We prepared weld joints by using this method, and again we have extracted specimen. This is the weld joint top view. Here we have made a buttering from both the sides using 309 electrode, and again we joined it using the same electrode, and we have extracted the specimen from the weld joint, and we have tested the spot wear resistant using spot wear resistant experiments in this region where this base metal dilution is expected in the buttering zone. So there we tested and we found that the results showed that there is significant decrease in the hot cracking sensitivity in the material. So this curve shows the susceptibility of total crack length without using the buttering layer. And this is for the nil dilution, that is at the center where there is no base metal dilution. And this is after buttering. We have seen that there is sufficient decrease in the cracking susceptibility in the weld joint. So this we could demonstrate, and just by modification of this step, by adding a buttering step to the, instead of directly joining the 304B4 base metal, we could greatly reduce the hot cracking susceptibility of the material using whatever available material, whatever standard available consumables with us. Without going for any borated or non-standard electrodes, we could achieve the weld joints without any cracking tendency. So here this is the microstructures taken after testing. We see that still this region, we can see that there is no cracking, where this is the weld metal zone, and this is the buttered zone. We see that it is cracking is because of dilution from the base metal. So these are the microstructure here. Though in the presence of borides, though we have delta ferrite, we don't see any beneficial effect, and it is like buttering only helps in reducing the hot cracking in this material. So finally, I'm concluding this talk. That is, base metal, whatever we are like evaluating from the base metal cannot decide the actual susceptibility during field fabrication, because that is how we have seen that during the base metal results alone cannot serve, because during field fabrication we have to go for different electrodes and for joining different components with going for autogeneous welding. So we have to go for consumable addition. So that is also important where this base metal dilution is concerned. So in case of this boron-free consumables, base metal dilution plays an important role for introducing cracking in the weld metal, and this can be avoided by adding suitable modification in the welding procedure, that is by adding a small step of buttering before actual welding process, and this is found to be very beneficial, and this is the way we have done this, solve this problem of hot cracking in the borated stainless steel. Thank you. Thank you, sir.
Thank you, madam. Thank you for your valid, highly knowledgeable, enriched talk on our boron added welding in our fast-breeded test reactor vessels and equipments. Thank you, madam. Wonderful. Any questions, please? If no question, we will move to the next item. I am requesting Tamil Nadu State Center for a small few minutes. We are likely to celebrate the World Habitat Day within few minutes. That is World Habitat Day. The theme of the World Habitat Day is mind the gap, leave no one, and place behind it. In that, we are having this is a theme what we are having in this year, and World Habitat Day is first celebrated on the Niobe on 1986 for shelter for right. Same thing, it is keep on increasing the shelterless people in from that our UN Habitat World Cities report is keep on increasing. That has to be reverted by our concentration on the habitat. So I am requesting the Professor Dr. Sakthivel for giving small lecture on World Habitat Day by a short lecture. Dr. Sakthivel, please, sir.
Yes, sir. Thank you. Thank you, sir. Can you hear me?
Yeah, hearing.
Right, sir.
Everybody's hearing, please.
Right. I'll share my screen.
Yes.
Yes. Thank you. Thank you. I once again thank the IEI KALPAKKAM chapter for giving me this opportunity. Can you see my screen?
Yes, sir. Shared.
Right. Okay. So my topic is engineers can make a difference to the world. This is a small short talk, and it is going to be an encouragement to all engineers, not only civil. Though I am a civil engineer, this will be an encouragement to all. I'm also happy to say that I am also a life member of IEI. So the topic is mind the gap, leave no one and place behind. That's the topic given for World Habitat Day 2022. First, I would like to talk about just 3 achievements made by engineers. The first slide, you see the Pantheon in Rome. It was designed by Apollo of Damascus in 120 AD. So it is approximately 2000 years now. It is still standing. And it is still the world's largest unreinforced concrete dome. Great achievement by engineers. Next, we see this lady with a prosthetic hand. Prosthetics, again, we have come a long way because of the help we received from biomedical engineers. But even 3000 years ago in Egyptian mummies, prosthetic toe is found. So it is a field which has been there, which has been developing now. Then This shows the submarine cable for the internet. The internet has changed our day-to-day life. Even a meeting like this is possible because of internet. We have, in the internet, we have the world's largest library, shopping center, video store, and communication channel, all rolled into one. And it was created by electrical engineers. Now, first let me talk about some important problems in the world. So these are the problems that cause a lot of stress and confusion. And we as engineers want to make the world safer, healthier, and a just place. And we always want to make a positive impact. Now, talking about water shortages, there is a lack of water, lack of access to good drinking water. And the problem is very acute in rural areas, because there people rely on open springs and shallow wells, which can be contaminated by animal waste and humans. Next, we talk about food scarcity. We all need a proper diet, and we need nutrition in our diet. So not enough food is available sometimes because of crop failure, droughts, and due to action by pests. And then we also have world hunger. Even though we are eradicated starvation deaths in our country, still there are starvation deaths across the world. And the number of people suffering from chronic hunger has climbed to, they say, 811 million in this year, 2022. And these are the problems. 50 million people across 45 countries are facing emergency levels. Food scarcity is caused by several reasons. Farmlands are increasingly being put to urban use. There is land grabbing. Land is acquired by private and usually outsiders. And then there are other reasons. Cultivation of land for biofuels instead of crops can also cause this. Then we have environmental degradation. We can look at water bodies in such a sorry state of affair. You look at this water body, water which needs to be clean is contaminated with a lot of garbage dumped into it. We have environmental degradation caused by deforestation, the felling of trees, desertification, and drought, land degradation, water and air degradation. Added to this, we have the problem of aging infrastructure. Infrastructure is designed with a particular, they are designed for 50 years, 100 years, and so on. But when that design age is reached, so we have aging infrastructure. Here is a picture of a bridge. This is a picture in Italy. The bridge collapsed. The bridge is called Ponte Morandi Bridge. It's collapsed in 2018. The reason was the bridge has reached its life and it failed there. And then we have aging infrastructure, dams, so many dams. They say 85% of dams. So this problem is more in the developed countries because they put up all these structures many decades ago. So many of them are reaching their lifespan's end. They say 85% of them are in the dams in the US are reaching their end of their life expectancy. They've already reached. In China, over 30,000 dams. In Japan, 60% of road bridges and 40% of tunnels are will become 50 years old. 50 years old is a milestone. And then we have lack of housing. So deficiency or lack of quality houses to accommodate the population. Then we have lack of transportation. So lack of transportation will result in an inefficient and unreliable supply chain, and it will always result in high overhead costs, and there could be damages in transit. Now I'm going to talk about some of the solutions to all problems, and all these solutions will be provided by engineers. We engineers will be providing solutions. We will be involved in different stages, in different capacities. Now the solution to water shortages would be constructing dams, reservoirs, aqueducts. Aqueducts is pipes or mechanisms to bring water. So we have the Krishna River, the Krishna project, where water is brought to Chennai from Andhra Pradesh. So there are other methods, desalination, water reuse. In all this, engineers will be heavily involved. Solutions to food scarcity. Now the talk is we'll have to grow our own food. We'll have to have terrace gardens, or we'll have to do vegetable gardens in our homes. We'll have to buy good thing to buy produce from local farmers, to plant fruit trees. And the solutions to prevent environmental degradation is to stop deforestation. Fines, and this is from the government side, fines and punishment for illegal dumping, and reduce unnecessary consumption, reuse and reduce waste generation, use public transportation. Then solutions to prevent environmental degradation. We can use, they are already being in use. Smart sensors are used in bridges, highways and railways for structural health monitoring. Bridges, we know, are designed for 100+ years, and their structural health is constantly monitored, so that any disaster like the one I showed earlier can be averted. Then we can have acoustic sensors to detect leaks in water lines. RFID tags. RFID is radio frequency identification. So we will work together with instrumentation engineers, electronic engineers, to make all these things possible. Robotics can be used for water supply and sanitation. And then smart traffic management using IoT, Internet of Things, can be done for the comfort of all. Then the use of public transport will be emphasized now, with a lot of public metro works and others in cities like Chennai. So usage of public transport saves a lot of money. We can save nearly 4 times savings is there. 1/4 the cost is involved if we use public transport. But the transportation has to be efficient, as it is in Singapore. We can avoid maintenance. If we have a vehicle we have to maintain, those things can be reduced. Parking fees, fines, etc. All these things can be reduced. Then smart sensors are used in bridges, highways and railways. For example, there is a bridge in Kolkata which opened. It's called Majerhat Bridge. So that bridge has sensors for structural health monitoring. So they always check how the structure is faring against static and dynamic vehicular loads. As I said earlier, we can have acoustic sensors to detect leaks in water pipelines. Smart traffic management. We see sensors here collect the data, and the computers control the traffic very efficiently. And the solutions to lack of housing are here. Again, we engineers will be involved in all of this. And there is a scope for all. So there will be, the government also will get involved, social and public housing, building smaller homes where we rent control. Government has to have a say on the real estate. Focus on the construction of affordable housing, etc., etc., etc. We all have a role to play in this. Living in rural areas should be made attractive, and that is already happening. People are commuting from rural areas to the cities. And the solutions to lack of transportation is development of additional road capacity, promoting the bicycle, efficient use of bus service, promoting bus transport, public transport in a big way, in a very big way, which is coming. And then lastly, I'd like to talk about smart cities. So in smart cities, advanced technology, data and analytics is used to improve the management of city resources and the lives of citizens. So data is gathered from a comprehensive network of sensors that can be transformed into intelligence that helps cities to reduce traffic congestion, commute times, to minimize energy consumption, lower pollution levels, reduce crime. The police will be happy, and all of us will be happy, enhance public safety, and achieve many other benefits. Through in smart city, all these are possible. And then in the smart city, there is an emphasis to grow food in the city. So even in heavily populated areas, some land can be used for urban farming. And this will encourage the establishment of gardens, so it makes the cities feel good. And the goal of today's architects is they don't say rural and urban. Now they want to bring about rur-urb. So you have a combination of rural and urban. Thank you.
Any questions, audience? If no questions, thank you, Dr. Samuel, sir, Assistant Professor, Hindustan Institute of Technology and Science. Thank you, Dr. Lenin, Coordinator, Student Chapter for Hindustan University, who joins hands with IEI KLC for celebrating World Habitat Day today. Thank you. I hand over mic to Honorable Secretary for vote of thanks on today.
Thank you, sir.
Sir, Samuel, sir.
Sir.
Sir, thank you very much for the excellent presentation. Your presentation is very, very excellent within short span, and you have done the nice presentation, sir. Thank you very much, sir.
Yeah, thank you, sir. Thanks, sir. Thank you, sir.
Thank you. Thank you. Thank you.
On behalf of our IE KALPAKKAM Local Center, we thanks one and all. First, we thanks to Chandramouli. It's a wonderful talk for sodium loop testing. And second one is Madam Divya and welding technology. And the third one is World Habitat Day by Samuel, sir. Thank you, sir. IE KALPAKKAM Local Center and IE Chennai chapter, Tamil Nadu State Center, and headquarters Calcutta, and council members all are coordinated for our IE KLC. So once again, I thanks one and all for the grand success this. Thank you, sir.
Thank you. Thank you.